Okay, so we'll start now. So yesterday we have started unit number 2. Okay, material testing and characterization techniques. Okay, so this is the syllabus of unit number 2. Okay, contents of syllabus, scheme content of unit number 2. Okay, and then we have discussed why tests are necessary, why usually material is tested. Okay, then there are two categories: destructive testing and non-destructive testing. In case of destructive testing, whatever specimen that you are using for a particular test, okay, that will be destructive, okay, during test. And in case of non-destructive testing, directly finished product is used to test, and no destruction will be there of the product. So you can use a ready product for the non-destructive test. So the first test that we discussed yesterday was tensile testing. Okay, so this is the tensile test specimen. Okay, it can be of a circular section, or it can be of a flat, you can say, or you can say a rectangular section. Okay, and it is actually held in a machine, ultimate tensile, ultimate testing machine. Universal testing machine, and in that there is an extensometer which is specifically used for a tensile test. Okay, and in that your specimen is held. Okay, and then load is applied to that specimen. So obviously after a certain time that material or that specimen is going to fail, and how it is going to fail. Okay, that we have discussed yesterday, first thing. The second thing, very important, is the during that fracture, or during that failure, whatever resistance that material shows to failure is nothing but the tensile strength. Okay, so on the basis of that test, this particular graph can be drawn. Now how this is done, that will discuss. That means we will conduct, or we will just discuss, just like practical for this tensile testing. I'm saying directly practical, so consider this as a practical session. Okay, so we'll conduct in 20 to 25 minutes, or we'll discuss in 20 to 25 minutes how this tensile testing is actually carried out. Okay, and how it actually works. Okay, how that actually making take place. Okay, how that material fails, that we'll try to discuss. Okay, first thing, I will repeat the procedure of the tensile testing, and then we'll go for that practical, okay, of tensile test. Whatever the specimen, it may be of rectangular shape or it may be of circular shape. Okay, it is fixed in a machine. Okay, so one end of that specimen will be held in a vise, and one end will be held in the holding system provided by that machine. Okay, and then after holding properly that particular specimen in the machine, what you need to do is you need to just apply a controlled load on that specimen. Okay, so obviously that load will be in newtons. Okay, so after applying the loads, naturally the material or the specimen will lead to extension. That means that particular material, that specimen will stretch. Okay, due to the force application. Okay, now in this case, if you apply a small load and if you release that load, that material will come back to its original length, or material will come back to its original shape. Now this happens due to elasticity, because every material have more or less elasticity. Okay, so that elasticity, or within that elastic limit, that material regain its original shape after releasing the load on it. Okay, now this is Hooke's law, because in this particular case, within this limit, we are getting stress is directly proportional to strength. Okay, this is first case, but this is not tensile test. We have to go beyond elastic limit. We have to enter into plastic deformation. We have to go beyond your yield point. You have to go beyond the tensile strength. Then and then only material will fail. If that material is not failing, that means you are not going beyond the tensile strength. Okay, so you have to cross the ultimate tensile strength of the material, so that the material will fail finally. Okay, so what you need to do is you go on increasing the load. As you go on increasing the load, obviously initially the material will be in elastic limit. After a certain time, it will reach its yield point, and we know that after yield point, what will be there? Material will leave its elastic limit, and it will enter into plastic region, or it will enter into plastic deformation region. Once it enters into plastic deformation, Now, even if you release the load on that material, that specimen, it will not regain its original shape. That means after elastic limit, whatever changes that has been taking place into that material, into that specimen, those changes will be permanent. And now the shape of that specimen is changed because we have entered into plastic deformation region. The specimen's shape is changed, specimen's dimensions are changed. This change is permanent now. Okay, still you need not to stop there. You go on increasing the load. After a certain time, what will happen? That material will stretch, and after a certain time, one point will come there which will result into stretching. That means stretching of that particular material will end. Okay, and necking of the that component, that specimen will start. Okay, after necking, after certain time, material will lose, or material will, rather, instead of losing, I will use material will end its resistance. Okay, resistance to that tensile load, and it will result into failure, or in other words you can say it will result into fracture. Okay, the fracture which is usually occurred in case of your tensile test is usually cup and cone fracture. But if you are using a ductile material, then and then only you will find this cup and cone fracture. This last sentence in this slide you can see over here, cup and cone fracture. Okay, so this cup and cone fracture is usually observed in materials which will show some ductility. If there is, suppose if there is a no ductility, definitely there will be brittleness. And if there is a brittleness, material will not fail in ductile manner. It will fail in a brittle manner. So that will be brittle fracture. Okay. So we are not going to check brittle fracture. We are going to check ductile fracture. How a ductile material fails. How it forms cup and cone fracture. That will discuss. So okay. So this is the graph that we discussed yesterday. Again, I am discussing in view of practical now. Okay. So this first straight line is nothing but the elastic limit or elastic region, you can say. Within this time, even if you release the load. Okay, 1 minute. Okay, so during this particular region, okay, even if you release the load, okay, it will regain its original shape, because this is a elastic, this is within elastic limit. After crossing this, there will be yield point, and after crossing yield point, there will be plastic region, or you can say plastic deformation. This deformation or this region will change the shape of the specimen, and that change will be permanent. After a certain time, there will be a tensile strength. Okay, and then finally, after crossing that tensile strength, okay, ultimate tensile strength, finally material will fail. So this end point shows the failure. Over here you can see in this yellow block. Okay, this is the failure, and this forms, if the material is a ductile, this forms a cup and cone type of structure, something like this. That's why it is called as a cup and cone fracture. Okay, so we'll try to understand this, okay, with a practical. Okay, is this video visible now? Is it visible?
No, sir, video is not still visible.
Okay, wait a minute.
Folders are visible.
Folders are visible. Folder is visible. Am I
Yes,
right?
yes, yes, sir.
Okay, wait a minute. Wait a minute. I will directly share the screen so that you will understand. It is started now, right?
Yes, sir. It is visible now.
Okay, okay. Now look carefully. I will speak in between. Okay, this video. I'll try to elaborate the things. Okay, it is self-explanatory video, but still I will elaborate in between. Okay, so try to concentrate on this. This is the tensile test video. Okay, this is as good as performing a practical. Okay, actually, see, the machine that we have is not advanced as shown in this video, but what you need to understand is the basic concept. Okay, because see, in case of the machine that we have, okay, we apply load manually. Okay, in this particular machine, it is directly computer controlled machine, and the load is applied through the programming only. Okay, so I will explain that. Okay, but you need to understand this is an advanced machine. Okay, basically.
The tensile test. First test, material with yield point phenomenon.
Okay, so two tests are conducted in this video. Okay, the first test is conducted for a material which shows yield point phenomenon, where it shows upper yield point and lower yield point, that kind of graph. Okay, it is explained in this video also. We'll elaborate that also.
In the first test.
Okay, so this is machine. Okay, wait a minute. Okay, this one is the machine. Okay, this one. Okay, and this machine is attached to this computer. So obviously the machine will be controlled by this computer. Okay, so whatever load that you are going to apply, whatever graphs that you are going to observe, okay, that will be observed in this computer. Okay, I mean on the computer screen. Okay, and the specimen that you are going to say fit, okay, or that you are going to hold in the machine will be in this these two wires. Okay, one is holding system and one is wires. Okay, so I will play this. So try to concentrate how the specimen is.
Tensile test, a plain carbon steel with yield point phenomenon is to be tested.
Okay.
This is the test.
Important now. See, this is the specimen. Okay, now this specimen have a circular section. If you see, the total length from this point, this gauge length in this particular specimen is kept as 100 mm. Okay, and after every 10 mm, one line is marked. Okay, you can see over here. Now this is to just to understand where exactly the necking is going to start, or how it is extended. That will be probably to analyze that. Okay, it will be easy if you mark such lines on the specimen, because see whether the stretching is more in this region or more in this region or this region or this region, that you can observe immediately after the test. Okay, so how it is done, that we'll see now.
Piece. It has a cylindrical test region with an original diameter of 10 millimeters and an original gauge length of 100 millimeters.
Okay, so this gauge length is 100 mm. Okay, and this diameter is 10 mm. Remember this.
Meters. Within this test region, distance marks have been drawn at regular intervals. They help to visualize and measure the plastic behavior of the specimen. Using a hand control, the tester moves the upper crosshead into its correct starting position.
Okay, so
now he can
machine is set now. Okay, to fit the specimen.
Place the threaded ends of the test piece in the lower and upper grips of the testing machine.
Fit the specimen into the machine. 1 minute. व्हिडिओचा जो आवाज आहे ओरिजिनल तो ऐकू येतोय का?
Oh, sir.
Yes,
Okay.
yes, sir.
Okay, no problem. Okay, we'll continue now. Okay, so it is fitted
In the
now.
next step, he swings the extensometer into its working position and checks that everything is correctly prepared. Then he selects all necessary
advanced machine, so certain sensors and everything is used in this machine. Okay, to get the accurate results. Okay,
testing parameters on the control computer. Ready. The test starts and the extensometer's sensor arms are carefully pressed onto the test piece. This way, the gauge length can be measured throughout the whole tensile test. The gauge length is displayed at the bottom right hand.
Okay, now this white colored, okay, on this right side shows the computer screen. That means the load that you are going to apply, okay, will affect this specimen. Okay, and how it is going to affect, the graph will be drawn on this this region, in this particular region. Okay, that means in this that may be the software of that particular machine. Okay, so in that software, the graph will be drawn here automatically. Okay, so you did not to do anything. Okay, you just increase the load. Okay, now concentrate on this. This is a computer screen and this is actual machine picture. Okay, so असं नाहीये की हे पॉज झालेलं आहे, हे चालू आहे, इकडे लोड अप्लाय केलेला आहे, and whatever the results are going to get, those results will be displayed over here. Okay, so try to look in both these, on both these windows. Okay,
corner of the screen. At the beginning, it amounts to 100 millimeters. During the tensile test, the test piece is slowly and constantly elongated with a standardized speed. The force that the test piece opposes to the imposed elongation is recorded and can be seen at the bottom left-hand corner of the computer display. The material behavior can best be observed in a force elongation diagram. The force F is being plotted upwards on the vertical axis, the elongation delta L towards the right on the horizontal axis. At first, the force rises rapidly. Force and elongation.
The load is applied now. Okay, so initially this line, okay, you can see over here this red line. Okay, it is a straight line because material is still in elastic limit. So it will show obviously a straight line. Okay, so as the load goes on increasing, what happens that we'll see now.
Are proportional and form a steep straight line in the diagram. In this area, the material behaves elastically. If the test piece were to be unloaded from this area, it would spring back completely.
Okay, आता अजून सुद्धा म्हणजे at this point also, if you release the load from this particular specimen, now it is stretched. Okay, हे असं दाखवते म्हणजे काय झालेलं आहे, on x axis it is elongation and on y axis it is force. So as we increase the force, the elongation is also there. It is elongation is taking place over here. Okay, so up to here, that means 0.1 and 0.11, you can see 0.11 mm elongation is there already. Okay, which is, and that means now this the gauge length of this specimen is now 101.11 mm. Okay, this is now this is not 100 mm now. This is 100.11 mm now, because this much amount of length is elongated. So that will be obviously addition into the total length of the gauge. Okay,
completely to its original length.
so go on increasing the
In
load.
materials with yield point phenomenon, the end of the elastic area can be seen clearly. The plastic deformation starts abruptly and
Okay, now at this point, that means almost around at 0.2 mm elongation. Okay, at force up to this 32. Okay, 32 kilonewton. The elastic limit has ended. Elastic limit of the this particular material has ended over here. Okay, and it has entered into plastic deformation. So suddenly there will be a drop in the load or drop in the force. Okay, now this is the behavior of the material. This is called as a yield point phenomenon. Okay, now if you see, this will be the yield point, but this will be upper yield point. Okay, and this force will drop down. Okay, to some up to certain extent. That lowest value of that drop is called as a lower yield point. Okay, so we'll see that now.
is accompanied by a sudden drop of force. If the test piece were to be unloaded now,
Okay, this point is upper yield point. This one, this top one. Okay, and this lower one where it shows a maximum value, or you can say the maximum drop or minimum value. This is nothing but the lower yield point. This phenomenon is called as a yield point phenomenon. Now at this point, even if you release the load, the material is not going to get its original shape. It's a total length at this point now. Is elongation is up to around 0.48 mm. That means it will be 100.48 mm. It is not now of 100 mm. It is of 100.48 mm. Okay, so we'll increase the load and we'll see what happens further.
now it would not spring back to the original length, but instead show a permanent elongation. In the next stage of the tensile test, an almost constant force level with slight fluctuations occurs. This phenomenon is called the ludas effect. After a certain strain, known as the ludas strain, the force increases again.
The force has started increasing again now. Okay, now this force, when force starts increasing, that means it is an indication that the material is approaching towards its tensile strength. Okay, ultimate limit. Okay, that means it is near about now. Okay, so we'll see
Material
that.
opposes an increasing force against the imposed elongation. It strain hardens. Up to the point of maximum force, the test piece is strained uniformly along its length. This means that the test piece gets longer and thinner, but keeps a cylindrical shape. As soon as the maximum force is reached, a neck begins to form at one point of the test piece.
Okay, now necking is going to start, but before that I would like to ask you one question. Okay, can anyone tell me from why, from this particular point, why the force has been increased? This was discussed in unit number 1 also.
Sir, because of permanent deformation.
Permanent deformation. Anything else? Any other answer? Yes. एक वर्क हार्डनिंग किंवा स्ट्रेन हार्डनिंग नावाचा एक कन्सेप्ट शिकवला होता मी, आठवतंय का? When material enters into plastic, when material enters into plastic deformation, okay, after certain time, it strain hardens, work hardens. That means its hardness increases. Okay, hardness of that material increases, and more amount of force, more amount of load is required in order to change the shape of that material. Okay, now for that purpose, if you see, after reaching this upper yield point, okay, suddenly the force has dropped. Okay, and it is almost constant with some ups and downs. It is almost constant around at 27.5, 27 to 28, between 27 and 28 kilonewton. It is constant up to this point. In this particular period, no doubt plastic deformation is taking place, but also it results into work hardening of the specimen, work hardening of the material. Okay, so this work hardening results, okay, leads to increase in the required load in order to change the shape. That's why from this point the load has been increased. Okay, so further this line increases the load, and as we have discussed in the procedure, the necking starts after a certain time. Now look at this particular picture. Okay, on the left side of this video. Okay, the necking is going to start where this arrow is showing. Okay, and at this particular point the necking is going to start. So how necking takes place, that you can see over here. Okay,
all further plastic deformation now only takes place at the neck, and eventually the test piece fractures there.
Okay, can you see here? The necking has,
Yes, sir.
the necking has occurred over here. Okay, you can see the cross section, or you can see the diameter is decreased at this point. Okay, the diameter of this okay is different, and this one is lower than that. Okay, this is called as a necking. Okay, so as you go on increasing the load, this necking will increase, and at certain point it will result into fracture. Okay, see this now. Okay, further necking is there. Okay, it is proceeded. Okay, more and more necking is there as you go on increasing the load, and this is failure. Okay, so I will just rewind this video for a few seconds. You just check how it
and
happens.
Eventually the test
right,
piece maximum fractures there.
Okay. The necking has started. Okay, the diameter is decreasing, and failure. Okay, so this is failure, this is fracture. So at this point, whatever the load that has been observed, okay, that you need to write down, okay, that you need to check out. After failure, if you see this graph, okay, after failure it has been reduced to this point. So immediately, obviously, the required load is 0 now because it has been fractured. So this line will come down to 0. And after starting of necking point also, if you see, there is a gradual decrease in the required load because there is a change in the cross section. So cross section is reduced, so obviously required load is reduced. So this required load is reduced, and at this point it has been fractured. So suddenly this load has come to 0. Okay, so see this further part of video.
In the recorded force elongation diagram, the force FEH at the upper yield point can clearly be seen. This is the highest force the test piece can sustain elastically. FEL is defined as the force at the lower yield point, Fmax as the maximum force. Using these forces...
Okay, so this is upper yield point, this FEH, and this FEL is nothing but the lower yield point. And this Fmax is nothing but the maximum load that you observed during this whole process. That means right from this 0 to this 0, okay, till fracture. The maximum load that was observed was Fmax, okay, this line.
The strength properties of materials can be calculated. The upper yield strength REH is calculated by dividing the force FEH by the original cross-sectional.
Okay, so upper yield strength is equal to upper yield point divided by original cross-sectional area.
Area S0. The lower yield strength REL is defined in a similar way.
Lower yield strength is equal to obviously lower yield point divided by original cross-sectional area.
The maximum force divided by the original cross-sectional area is called tensile strength.
And this is your tensile strength. So tensile strength is equal to maximum load that has been applied divided by the original cross-sectional area. Okay?
Rm. In the last step, the tester swings the extensometer back into its resting position and removes the broken test piece. On the work table, he puts the fragments back together again.
Okay, so this is your broken piece. Now, this has been stretched, okay, because now in the next part of this video, the original piece will be kept over here, okay, so you can just compare.
With the help of the distance marks, the percentage elongation after fracture can be determined. This is the permanent strain after fracture and amounts to about 30%.
Okay, so this was the size of our original specimen, and this is the fractured specimen. So you can see the elongation has been there, okay, the stretching of that specimen, okay, you can see. So almost 10-20 mm has been increased, okay.
This example. Please note that the percentage elongation after fracture depends on the length to diameter ratio. By measuring the smallest diameter at the point of fracture, the percentage reduction of area can be calculated. It describes the reduction of cross-sectional area at the point of fracture in relation to the original cross-sectional area. In the second tensile test,
second material is without yield point, without yield phenomenon. Okay, म्हणजे तो जो upper yield point and lower yield point जो phenomenon होता, that will not be observed in this material. Okay.
Material without yield point phenomenon is to be tested. In this case, it is a precipitation-strengthened aluminium alloy. The test piece has exactly the same shape and dimensions as the specimen in the first test. It is cylindrical, with an original diameter of 10 millimeters and an original gauge length of 100 millimeters. After fitting the test piece into...
Sorry, the material different hai na?
Oh, material is different in both the cases. Okay, in the first case, the material was plain carbon steel, which usually shows higher ductility. Okay, and it is a soft material. Okay, in case of this aluminum alloy, it is usually shows lower ductility and more brittleness. Okay, not more brittleness in the sense not higher brittleness, but comparatively it has more brittleness as compared to the plain carbon steel. Okay, and yield point phenomenon is different in this particular material. It will not reach to upper yield point and lower yield point. Nothing will happen. Okay, it will reach its upper yield point and then it will directly start its plastic deformation. It will not come back to its it will not come down to its lower yield point. There is nothing like that, no lower yield point and all these things. There will be one yield point only. Okay, and that will be the yield strength of that material. Okay, you will see that during this particular experiment.
The extensometer into its working position, the test can start. The initial linear curve in the force elongation diagram again shows the elastic behavior of the material.
Up to a certain extent, there will be obviously elastic limit.
But this time, the end of the elastic area is not revealed by a sudden drop of force or any distinct change.
Okay, so there will not be any kind of sudden jerk of force or sudden drop of force. Okay, it will directly, you can see over here. This one is the elasticity. Okay, up to here. Okay, or somewhere over here, yield point will be there, and after this yield point, it will directly enter into plastic deformation. So there will not be any type of drop in.
There is a smooth and gradual transition from linear elastic behavior to plastic deformation. In the further course of the tensile test, the force increases and the test piece again is strained uniformly along its length. At the point of maximum force, a neck develops, and all subsequent plastic deformation is confined to this neck until fracture finally occurs there.
Okay, at this point it will fail. Now you check, there is no necking. Okay, there will be necking, but that will be a very, very small necking. Okay, unlike the last piece. Okay, you can see over here.
As a common substitute for the yield strength,
so this will be graph for the materials which do not show yield phenomenon. Okay,
0.2% proof strength is used. It is the stress that causes 0.2% of plastic deformation in the material. And this is the way to calculate it. First of all, the elongation that corresponds to 0.2% of strain has to be computed. For an initial gauge length of 100 millimeters, the result is 0.2 millimeters. In the force elongation diagram, a straight line parallel to the elastic line is drawn through the offset point of 0.2 millimeters of elongation. The force at the intersection point of the offset line with the force elongation diagram is designated as Fp 0.2. This is the force that causes a plastic strain of 0.2%. The 0.2% proof strength, Rp 0.2, is equal to Fp 0.2 divided by the original cross-sectional area S0. Tensile strength, percentage elongation after fracture, and percentage reduction of area are calculated in the same way as in the first test.
Okay, tensile strength calculate करायचा formula same आहे. Okay, या याच्यामध्ये पण same formula use करायचा. फक्त fracture is different in both the cases. Okay, all of you understood this?
Yes, sir.
Okay, so it is very easy. म्हणजे tensile test म्हणजे काही फार अवघड नसते. You will repeat these things in your SOM also. Okay, so in the solid mechanics नावाचा subject आहे ना तुमचा. In that subject also you will go through these tests. Okay, nothing difficult is there in these tests. Okay, but as far as this video is concerned, two materials are tested. Okay, first one was showing some ductility, so that there was a yield phenomenon, there was upper yield point, there was a lower yield point, everything was there. Okay, in the second material there was little bit low ductility, and so that particular material wasn't showing any kind of yield point or sorry yield phenomenon. So as you go on increasing the load, at certain point it will leave its elastic limit and it will directly enter into plastic deformation. So during this transfer, okay, there will not be any kind of jerk in the force. Okay, so that is the specialty. Okay, So this is about tensile test. Okay, this you can consider as a practical. I will share the PPTs, no doubt about that. So on the basis of that, you can complete the assignment work of this particular experiment. Okay, or you can say it's a write up of this particular experiment. Okay, clear? Now what you have
Yes,
to
sir.
do is I have provided you a second link. Okay, so just join that second link. Okay, within a minute, and we will start our regular lecture. Okay.